So today we're going to talk about similar shapes and do it in a way so that students can understand what it means when two shapes are similar and what's the difference between similar shapes and non-similar shapes. Sometimes for kids, they can look at two shapes and assume they're similar because they look the same or whatnot, but based on the actual length of the shapes and the angles, they could not be similar at all. So we're trying to provide a way for students to figure out if the shapes are in fact similar to each other. So first we have the mathematical goal, which is going to help support the students' understanding of similar shapes using a visual representation of what I have created, and use the equation to help determine if the shapes are in fact similar or not. We have our pedagogical goal, which is for similar shapes. Most teachers just give the formula of how to find if the shape is similar or not without really going into too many examples and doing it with them, where students need to be taught and kind of do it with the teacher at the same time. So in order for students to be able to differentiate between the two, they need to get a concept and an understanding of both examples. So some things I could ask during class would be like, do these shapes appear similar or not, and why? So that kind of helps the students look at them and get a pre-guess to see if they are, so to see if they're heading in the right direction, but to formally use the equation to determine the final answer. What is the formula for finding if the shape is similar and how do we use it? That's just to gauge the understanding of the formula I'm going to show, and so that they're able to use it on their own and find if the shapes are similar. And like, what is the definition of two shapes being similar mean? The technological goals, I would like to have the students doing the assignment with me. So if I'm doing it on the board, I would like them to be at a computer following along and doing it at the same time so that they can engage in understanding. And students learn best anyways when they're doing it at the same time, and instead of just watching and then trying to remember it later. So I would hope that they could be provided with computers to follow along, and then using the examples we can decide if the shapes are similar or not, and then hopefully the students can make up their own examples using this software, and then switch with a partner and see if the partner can figure out if the shapes are in fact similar. So for our similar shapes are two shapes are similar if the only difference is their size. So I have an example of similar shape right here, but I'm going to prove to you that it is a similar shape using the equation and to find out if it is indeed similar, even though we already know it is. So we have our square ADBC and our other square WZ, X, and Y. We see that the size of this small square is 1.5. The size of the big square is 3. So we already know we're going into it with the notion that it is similar. But just to double check, we need to tell the students that this side equals this side. The sides need to stay the same when working it. So side DB cannot go with WY. The students will get confused if we try to do that, even though technically, since it is similar, they work back and forth, but we should tell the students that dB is equal to zx just because it's staying on the same side of each other, and therefore we see that this side is equal to this side, the bottom is equal to the bottom, and so on and so forth. So to do the equation, a way to figure out the equation, we can either put this on top or we can do this, but we make it into a fraction or a division problem and try to figure out what it equals. So we have side DB is over ZX, BC is over XY, CA, YW, and AD is over WZ. So we get our equation of 3 over 1.5 equals 3 over 1.5 equals 3 over 1.5 equals 3 over 1.5. And if we do 3 divided by 1.5, we get the answer of 2. And we know that all of those equals 2. Therefore, the big square is similar to the little square, and the big square is double the little square, which we see because all of these are in fact the same. So here's another example where I used rectangles. And so we want to try to figure out if these two rectangles are in fact similar. To most kids, after using this, they might think that they are similar because they look about the same or they're the same shape, but are they in fact similar? Does this side and this side equal the same as this side and this side? And that's what we need to find out. So I already got the distance measurements of all the sides, and we find out that KL is 6.38 centimeters and PQ is 4.21 centimeters. So in order to find the equation, we kind of do it like how we did the equation over here, where we put one on top of the other. And it doesn't really matter which one goes on top, as long as we're consistent and the smaller side goes on top or the bigger side goes on top for every one of the division problems. And then also to figure out if they're similar, we also need to take the sides of these to determine if they equal each other, to see if maybe like this one, it's twice the size, 3 times the size, or whatever. So we did the equation. We have KL over PQ equals LM over QO. And so we get that KL, like we said, was 6.38 centimeters, and PQ is 4.21 centimeters, which equals, when we divided, 1.52 centimeters. Now, for LM was 2.48 centimeters, and QO was 1.03 centimeters. Well, that equaled a 2.39 centimeters. So we see 2.39 does not equal 1.52. So even though they might look about the same, they are in fact not similar because they are not equal to the same. 1.52 does not equal 2.39. So since they are not equal, they are not similar. Now we will try one more example using triangles. So this is a little different. So we've showed an example of similar shapes and non-similar shape and how to differentiate between the two using our equation. And now we're going to do one more example to help students find out sides using similar shapes. So telling the students beforehand that these are similar shapes, we know that RT is 10 and GI is 5, IH is 4, but TS we're unsure, that's X. So we're trying to figure out what X entails. Well, we can use the same equation that we used before, where we put one over the other, make sure it's consistent. So we can put 10 over 5 and X over 4, or we could even put 10 over X or 5 over 4. We just have to make sure that we're using the same thing for consistently. So what I did here, I actually put GI over IH and then RT over TS. So we have 5 over 4, okay, and we have 10 over X. Well, in order to find X, we need to cross multiply. So 4 times 10 and 5 times X. So we get 40 equals 5X. Well, then we have to figure out what X equals. So in order to do that, we have to divide both sides by 5 to get X standing alone. And we know 40 divided by 5 equals 8. Therefore, X equals 8. So now we know that because these two triangles are similar, and because we've learned the equation and how to differentiate between the two, we can now be able to find side lengths if we're given 3 other sides. So I hope this helps in how to differentiate between similar and non-similar shapes.